Okay, so air conditioning is dealing with air, right? Which air? Is it dry air? No. We know this air consists of dry air part plus there is water vapor in it. So in combination, we call it moist air. Okay. So the air conditioning system is specifically designed to treat this air, right? Not only to maintain proper temperature, but also relative humidity. Also, of course, velocity, motion, we need to clean it, etc. But these are the two main things. The two major tasks or functions of any air conditioning system is to maintain a proper temperature and relative humidity or humidity level. So the study of air properties means dry air plus water vapor is called psychrometry. So with the help of psychrometry, we can design air conditioning systems. Okay. So this chapter is mainly covered from this book, Edward G. Peter, and also from the Stoker and Jones. Okay, and some other books can be used as a reference. This book is mainly English units book. This one is SI unit. So the practice problems I have taken only from this book, Stoker and Jones, but the problems which you will see in these slides, they are from these books, Edward G. Peter. Okay. So let's start this chapter. So actually we already covered its basic theory in Thermo 2, if you remember, the last chapter was. So that is again repeated here. So I will quickly go through that part. So what is atmospheric air? It is very clear. Okay, this atmospheric air is the environment in which we are living, and that is the environment of every air conditioning system, which it is trying to maintain. Atmospheric air consists of dry air plus vapor, so that's why we can use this term moist air. And technically, we should call it moist air. Right? It's not perfectly dry. It's not all water, of course. So it's a mixture. So this atmospheric air is actually consisting of a mixture of gases, which is air plus water vapor. And of course, there are pollutants in it also, dust particles and other unwanted material in it. And these pollutants we must filter out, right, before sending this air into the room to be air conditioned. So psychrometry or psychrometrics is the study of properties of this mixture of air and water vapor. That is called psychrometry. Okay, so that is clear, because amount of water vapor changes in that air, right? Because continuously there is evaporation or condensation going on, right? At some places inside this air conditioner, whatever cold air is coming in contact with this cold surface, some of the moisture is condensed out. But at the same time, water is evaporating into that air from different sources, oceans, lakes, rivers, showers, even our human body, we are adding water vapor in that air. Okay. Not only from sweating, but also during breathing, we are adding water vapor. Okay. So this water vapor which is present in that air, that is a major factor to define human comfort and to design these air conditioning systems. Those are not something which we can neglect. The effect of water vapor becomes very critical whenever we are dealing with air conditioning systems. Okay. So the temperature of air which we are dealing in air conditioning system, what is the minimum and maximum temperature range? in any air conditioning system, that will be between these two values. In air conditioning system, we are not dealing with air higher than 50 and we are not dealing with air below -10. It is always between these two limits. So in these two limits, what about the CP value of air? And this air can be treated as an ideal gas, number one. Secondly, this temperature range is so small that we can assume CP as a constant, which we are doing so far. Okay, in SI unit, and that is in English units, right? So here you see CP of air as a function of temperature from -10 to 50. So that is only in the third decimal you have some difference. So it's about 1.005 we can take normally. Okay. What about enthalpy of dry air? Dry air means without any water vapor. So enthalpy, we always take some reference to define enthalpy. So actually it is Cp dt. But here one of the T is 0 degrees Celsius. Here he is specifically mentioning Celsius. Whenever there is dt, Celsius or Kelvin doesn't matter. And one of the T is 0 degrees Celsius. So that's why it is not writing dt, because one of the T is 0, the other is any other temperature. So in this equation, when I am writing dry air enthalpy as Cp dt, but only T means the other T is 0 Celsius. So it means this single T which is left here, it is Celsius also, right? Cp dt, because in dt you have two T's. Add 73 here, 273 here, those will cancel. Okay. So single T which is remaining, it is Celsius now, not Kelvin. Okay. So you must be very clear about it. Okay. So that is the enthalpy at any temperature with respect to 0 degrees Celsius. And the enthalpy change anywhere between this, in this range, is given by Cp delta T.
I'm saying like the test.
Yeah.
Like the test.
Like the test, which test? Yes, in the test it was Celsius. Okay. Like in that test. Okay. So 1.005 into delta T. That can be used to find out the enthalpy of, no, look, dry air. Now we are not talking about moist air, only pure dry air part. Okay, so because in air conditioning processes, we will not be concerned about enthalpy at one point. We are always interested in enthalpy change from here to here, or from here to here, or from here to here. So that's why we'll be dealing with delta H, not just H. Okay. This water vapor which is present in that air. Now we are saying this air is ideal. What about water vapor in that air? Can we treat it as an ideal gas or not? That is the question. No. We have discussed it in thermo too, but I think majority have forgot. Generally speaking, yes, you cannot treat water vapor as an ideal gas, but we can treat a gas as ideal gas if its pressure is very low. At very low pressures or at very high temperatures. Again, chapter 3 of Thermo 1, properties of pure substances, that chapter. So if you revise that chapter, you will know that at very low pressures, a gas can be treated as an ideal gas. Now, how low pressure? If I remember that thing, 10 kilopascal. Below 10 kilopascal, water vapor can be treated as ideal gas. Now, what is the water vapor pressure in air? That is normally less than 10 kilopascal. Water vapor in that air. Okay. So that's why, because water vapor pressure in that air is normally less than 10 kilopascal, that's why we can treat water vapor also as an ideal gas, and we can use PV is equal to RT or PV is equal to MRT for water vapor present in that air. Okay. So this atmospheric pressure consists of two parts. One is pressure due to dry air and second pressure due to water vapor. So the total pressure of atmospheric pressure is actually consisting of two parts, dry air part and the vapor part. This does not change a lot, but this is changing all the time now on the surface of the earth. Yeah, as you go away, of course, this one is also changing, but we are talking about when we are on the surface, sea level. Okay, partial pressure of water vapor, we also call it, because now the total pressure consists of pressure of dry air, pressure of water vapor, and pressure of water vapor is also known as vapor pressure. Okay. Okay. Now we've said that the maximum temperature in an air conditioning system is 50. In that air conditioning system, where you can expect 50?
The condenser?
Yeah, in the condenser, not here, right? So we are talking about both condenser, evaporator, the entire air conditioning system. Okay. At 50 degrees Celsius, why water is vapor? This is 50 degrees Celsius temperature line on TS diagram. Why water is vapor? Because on 50 degrees Celsius, what is this thing? What is this? Pressure. Okay. At 50 degrees Celsius, water will be gas if it is here, 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 here. These are the possibilities for water to be gas at 50 degrees Celsius. And what are these pressures? These are lower than, what is this pressure? I am showing only water here. This diagram I have shown only for water. Water is vapor at 50 degrees Celsius. Why? Because what is this pressure? Saturation pressure corresponding to 50. So it means all these pressures are lower than P set, right? So it means water vapor in that air at 50 degrees Celsius has a pressure lower than P set. And what is P set? 12.3 kilopascal it is shown for water. So it means all these pressure lines, they are lower than 12.3. So this is such a low pressure, water can be treated as ideal gas. Okay. For lower temperatures, for example, at this temperature, for example, 10 degrees Celsius, pressure is even lower, right? So that's why in this entire range of pressures, water is treated as, because water is gas in that air. Okay. So water vapor is an ideal gas. So the enthalpy of water vapor, that is the main thing. If we show enthalpy lines on this TS diagram, which we normally do not show, but if you show enthalpy lines, they look like this. When you are below 50, enthalpy lines are just horizontal in gaseous region. Above 50, they are a function of pressure also. But below 50, they are only a function of temperature. For one particular temperature, enthalpy is constant for water. Okay, because if again from thermo 1, enthalpy is only a function of temperature for ideal gases, not pressure, only temperature. So water is behaving like an ideal gas, and that's what we see. That enthalpy is only a function of temperature. right? So if you know the temperature, now this enthalpy can be taken as this one, because this one is almost equal to this one. So enthalpy anywhere in the vapor region can be taken as enthalpy at this point, at that temperature, at that temperature. So enthalpy is only a function of temperature. That's why we can write this thing. Enthalpy of water vapor at a particular temperature when pressure is very low can be taken as Hg at that temperature. Okay. Okay. Now, what is the enthalpy of water vapor at 0 degrees Celsius? Water vapor means this is Hg. That is about 25. Now, we are in this range. Now, when the water is superheated, so again, I have to shape like this TS diagram. So that is 50 degrees Celsius. Here somewhere you have 0 degrees Celsius. Okay. So at 0 degrees Celsius, this Hg is this much, 2500.9. Okay. Now in this region, in this entire region, Cp of water can be taken as 1.82 in the vapor region, pure vapor region. Because in the air conditioning processes, some process will be here to here, or here to here, or here to anywhere in this region in the air conditioning process. Or maximum we can reach here when water is condensing. So we are in this region. For this entire region between minus 10 and 50, let's take Cp as Cp of water vapor, 1.82. Okay. So I can find out water vapor enthalpy Hg plus Cpt. Hg till this point. Now here Hg is shown only for 0, but between 0 and 50, all these Hg values are very near to each other. Hg. But now if you go further, now you have to add Hg plus Cpt. This is saturated, but now from saturated to superheated, you have to add CPT. Now what we can, this is, okay, if you do not want to use that assumption, use table. Okay. If you do not want to use table, we can use that assumption to find out enthalpy at any temperature T. That represents Hg plus Cp at any temperature T. Okay, actually it is dt, but we are showing it with reference to 0. So look here, the remaining T, it is specifically mentioned here. If it is not mentioned, then you can think it's Kelvin or whatever. But here it is specifically mentioned that in this equation, actually it is delta T, but one of the T is 0 degrees Celsius. The second T is also in Celsius.
So between minus 10 and 50, I can take the CP 1.8.
Yes, in this region, if you are in the superheated region. Okay. So that is an assumption for this chapter. If you do not like this assumption, okay, then use the steam table every time at that pressure and whatever temperature. Okay, otherwise we can use that. So that is in kilojoules per kilogram. The second is BTU per pound. The same thing is shown in English units. Hg plus Cpt, where here T is in Fahrenheit. Okay. Here using this equation, here are the enthalpy values at any temperature. Okay. And these are the enthalpy values from the table, steam table, and these are the enthalpy values using that equation, which we have just shown. The difference between them is so small that it is negligible. to find out enthalpy in the superheated region. Okay, in this temperature range. Okay, so either use table or use this equation. But in this chapter, we will be studying psychrometric charts. So most probably you will be using only psychrometric chart. Okay, there will be as such no need to read these values from tables maybe. Okay, now let's go through all the basic definitions which are required to do psychrometric calculations. All right, what is dry bulb temperature? Yeah, we already discussed in Thermo 2. Let's do it again. So if you measure the temperature of this normal air with a normal thermometer, whatever temperature you will get, that is called dry bulb, because bulb is dry. It is not wet. Now, if you cover this with wet cloth like this one, now if you measure the temperature, this will be less because now water is evaporating. Okay. Now, what is the minimum temperature you can get in that air? Make it like this.
Make it flow.
Yeah, make it, or either make the air to flow over it or make this thing move in air. So you will get the minimum possible.
So you will get more.
Yeah, you will vaporize more. So whatever is the capacity of that air to absorb that water vapor, it will evaporate and you will have, so when the water is evaporating, what is it doing? It is absorbing heat, right? So that's why the temperature of the air will drop, because it is absorbing heat from that air, all right? So that's how we can find out dry bulb temperature, either using this, or here you see a setup. This thermometer is exposed to the airflow, and this will give us dry bulb temperature, and this will give us wet bulb, because here the bulb is covered with a wet cloth, a wick. Okay. So it means wet bulb temperature will always be less than dry bulb temperature. If this air is very dry, then the amount of water vapor which will be added to the air will be more, because air is already very dry. It has the ability to absorb more water vapor. So the more water will evaporate, the lesser will be the temperature. Okay. So wet bulb will always be less than dry bulb, but wet bulb may approach to dry bulb temperature if this air is already very humid. It's already very humid, it cannot absorb more water vapor. So here the evaporation will be less. So less evaporation,
This time.
less drop will be the wet bulb in the wet bulb temperature. Okay, so by measuring dry bulb and wet bulb temperature, we can tell about the humidity of that air. How humid is that air? So this is what normally we measure. With the help of these dry bulb and wet bulb temperatures, we can find out all other properties, specific humidity, relative humidity, which we will now discuss. So in all those weather data stations, what they are doing, they are measuring these two temperatures, dry bulb and wet bulb. Based on this, they find out how humid is the air. Right?
The difference.
Yeah, the difference, but how to convert it in humidity, we'll see now. Or those psychrometric charts which have been developed. So if you know dry bulb and wet bulb, you will have a point. Now you can read how humid is that air. Okay. So these two terms are clear. Here is the explanation. So using such experimental setup, what we are trying to do, we are making this air fully saturated. We use the term saturated here. It doesn't mean boiling or condensation. Here saturated means here air when it is fully saturated means the maximum amount of water vapor which it can hold, it has in it, then we call it, it is fully saturated air which is leaving here. It was dry air entering, now it is fully saturated air. So it means this temperature is dry bulb temperature of that air, and this will be the wet bulb temperature of that air when this air is fully saturated with water vapor. Okay. So wet bulb simply means when this, because you will wait until this temperature does not drop anymore. It means now maximum evaporation has occurred. Now air cannot hold more water vapor. So that's why when it is very humid outside, uh, even our sweat doesn't evaporate, right? When it is already very humid. Okay. Okay, so it means wet bulb temperature can never be higher than dry bulb temperature. That is not possible. Wet bulb temperature will always be less than dry bulb temperature. Okay. Then there is another term which is called dew point. Dew point. Okay. Here you see, for example, this is the dry bulb temperature of air. For example, 50. This is the temperature of air. And it is also the temperature of water present in that air. Okay. Now, if you cool this air, just cool, sensible cooling. Sensible cooling means amount of humidity remains constant. So it will follow this line. This is the vapor pressure in that air because there is water vapor in it. Due to this water vapor, there is a vapor pressure. Now, if you cool this air, it will follow this line, constant vapor pressure of water until this point. At which the same air becomes fully saturated. Because for this pressure, there is one saturation temperature. Here it was superheated, now you are cooling it until it becomes fully saturated. So this is the point which is called dew point temperature, at which this water vapor will start to condense. Clear?
So you mean it's saturated point. The air cannot carry
More water vapor in it. So if you further cool it, this water vapor will separate. Okay, so it means here this, now you can do two things to take the water out of this air, either by cooling it. What is the second option? If you want water in that air to be condensed, that is one way, cool that air. Second way, if you add water vapor, means pressure is increasing at the same temperature. If you are not cooling it at the same temperature, if you start adding water vapor until you reach this pressure, now you cannot add more water. If you will try to add more water, that will condense immediately at the same temperature. Okay, so if this concept is clear, then you can understand what this means. Dew point temperature. That's what we observe, right? When air comes in contact with a very cool surface, so it means its temperature is suddenly dropped to such a low value at which it will start to condense. The water vapor present in that air will start to condense. Okay, and the same is happening in these air conditioning or refrigeration systems. This is the indoor unit or inside the cabin of our household refrigerator. So this ambient air, when it comes when in contact with the very cooled surface, so the water vapor present in that air, maybe it's this temperature is lower than its saturation temperature. Okay, so that's what we see. That's why water is condensing out. Okay. because this temperature is less than or equal to dew point temperature of water vapor in that air. Okay, that is clear, hopefully. So now we have discussed dry bulb, wet bulb, dew point temperature. What else? Humidity ratio. What is humidity ratio? For example, here we have air. In that air, these are, for example, water vapor molecules. Okay. So the amount of water vapor, m of V divided by m of air, dry air, uh, dry air. Total is mv plus m of dry air. Right. So if we divide this mv with mass of dry air is called humidity ratio or specific humidity. Okay. Kilograms of water vapor per kilogram of dry air or pounds of water vapor per pound of dry air. That is called specific humidity or humidity ratio. Okay. For example, here you see air at 70 degree Fahrenheit. If it has this much pounds of water vapor in it, in 1 pound of air, if there is 0.015 pound of water vapor in it, so how we will define humidity ratio?
0.015
Over 1 pounds of water vapor per pound of dry air. That is called humidity ratio. Okay. Now see, because 1 pound is such a big unit, now this is a very small number compared to 1 pound. So what we do, we normally use this terms, grains. We multiply with 7,000. So we will represent this humidity ratio as grains of water vapor per pound of dry air. In 1 pound, there are 7,000 grains. Okay. In chapter 9, which we already covered, we use this thing. Okay. Okay, now here is important thing. So this air was at 70 degrees 70 degree Fahrenheit, the same air at 70 degree Fahrenheit. Now from here to here, what is the change? Same 1 pound of air, same 1 pound of dry air, but the water vapor is changed from 110 to 55, almost half. If temperature is constant, then what we can say, here, for example, this was the maximum capacity of this air to hold this much water vapor in it. How much? 110.5 grains. This was its maximum capacity to hold water vapor in it. So that's why we call it 100% saturated air. Same air, same temperature, but now the water vapor molecules are dropped to half, 55.25. So then I will call it, it is 50% saturated air. Okay. So based on this, we can define another term which is called relative humidity. Just see in this example, this air at 70 degree Fahrenheit, it can hold maximum this much. And actually, for example, it is holding this much. So actual water vapor divided by maximum possible water vapor at that temperature is called relative humidity. So what is specific humidity? Water vapor divided by dry air. And now what is relative humidity? Water vapor actual divided by water vapor maximum at a given dry air temperature or atmospheric air temperature. That is relative humidity. Water vapor actual divided by water vapor maximum at that temperature. Okay. For example, now here, see, this water vapor at 10 degrees Celsius is 100% relative humidity. What this mean? This is the maximum amount of water vapor this air can hold. Same air, if you increase its temperature, same air. So the same water vapor is representing 52% relative humidity. Because as you increase the temperature of the air, its ability to hold water vapor increases. So look, uh, specific humidity is not changed from here to here. What has changed? Relative humidity. Specific humidity is same water vapor, same air, same air. But here air temperature was 10, now here temperature is 20. Specific humidity is same, but relative humidity is changed. If you further increase the temperature of the same air, relative humidity will further drop. So this difference should be clear between specific humidity and relative humidity. Let me explain it in a different way. Let's use this chart. TS diagram. This is, for example, 50 degrees Celsius. This is, for example, 10 degrees Celsius. Okay. Here is the water vapor pressure in that air. This is actual, this is maximum possible. If I show a similar point here at a lower temperature, this is maximum water vapor, sorry, actual, and this is maximum possible. After this, it will condense. If I show a similar point here at a lower temperature, now the distance between these two is very small. So here you have higher ability to hold water than here at lower temperature. So we can understand the same thing with the help of TS diagram. Okay. So then there are some more terms. Now we have seen dry bulb, wet bulb, dew point, specific humidity or humidity ratio, and relative humidity. Next is specific volume. It's simple volume of air per unit mass. Okay, he's using weight, but actually it's mass. Okay. So volume of air per pound of air, or meter cubes per kilogram of dry air. That is called specific volume. Then enthalpy, that is very important term. Enthalpy of this air per unit mass of dry air. Okay, let's discuss this in more detail. Specific enthalpy, H, enthalpy of air per unit mass of dry air. And what is enthalpy? Enthalpy is energy content U plus EV. Saturated air, I just told you what is meant by saturated here when it absorbs maximum possible moisture. Okay, that is called saturated air.
Maybe hold.
Yeah, which it can hold at a particular temperature. Okay. So the condition when air contains maximum amount of water vapor which it can hold, that is called saturated air. And this depends upon air temperature. As the air temperature increases, its ability to absorb moisture is also increases. Okay, now we want to find out these air properties. Both dry air and water vapor in atmospheric air, both are acting like Ideal gases, dry air part and also vapor part we discussed already. So that's why I can write this for dry air part. A here means dry air. PV is equal to MRT and R of dry air is this much in English units. In SI unit, it's 287, remember, or 0.287. Now it is in English units. Similarly for water vapor, this is the R of water vapor, but all in English units, okay? So these are the ideal gas equations where we have replaced R value, the rest is same. Now let's define again those specific humidity, relative humidity in terms of equations now. First we understood its definition, now let's write its equations. That was specific humidity, mass of water vapor per unit mass of dry air. Okay, now I can replace this m of W and m of A using that ideal gas equation, mass of water vapor or mass of air. Okay, in one book he is using V for water vapor, in the other book is using W for water vapor. Okay, so this is clear from ideal gas equation. Same volume, same temperature, put the value of RV of water vapor and RA of air, pure air. This is what we will get. Now put the value. This is the equation to find out specific humidity. Okay, if we know the pressures of water vapor in it and pressure of air, ambient, atmospheric, sorry, dry air, so we can find out the specific humidity. What is this PA here? Pressure of dry air. So what is the total pressure? PV. So I can write PA as P total minus PV. Okay, so we can write the same equation like this. So specific humidity equation in terms of pressures, total pressure or dry air pressure and vapor pressure. Okay, so where P is the total pressure. Okay, where P is PA plus PV. Or we can also, these are the equations which we saw in the previous slide in terms of English units. Okay, to the same, you will get the same number. Whether English unit or SI unit, this ratio will be same. This one. Okay, same equation. To find out specific humidity, now in our old thermo book is using omega, in this Edward G. Peter book is using W. So it's the same thing, specific humidity. Let's do one problem. The partial pressure of the water vapor, how much is the time? 38. Okay. The partial pressure of water vapor in the air is 0. Partial pressure of water vapor, so it is PV. When the barometric pressure is what? P total. Okay. Find the humidity ratio. So now we have the equation, just put the values. Here is the equation. Find out PA. Put the value, that is specific humidity. Now this here is PSI, so that's why we get pounds of water per pounds of dry air. If you want to write it in terms of grains, because this is a very small number, multiplied by 7,000. So that will give us grains of water per pounds of dry air. Okay, so now we have this equation we just saw. Specific humidity. Similarly, now let's discuss relative humidity and its equation. So let's again see here, you have total mass of air 1 kilogram. For example, in that air, there is 0.01 kilogram of water vapor. And what is the maximum possible? For example, maximum possible is this one. So now I can define specific humidity and also relative humidity. What will be specific humidity? The ratio between these two. And what? Yeah, mass of water vapor divided by mass of air. And what will be the relative humidity between these two? Actual mass of vapor divided by maximum possible. Okay. That is specific humidity and relative humidity. So that's how we define relative humidity, mass of water vapor divided by same mass of water vapor, but maximum possible. So here again, we can use ideal gas equation, but now it's all water divided by water. What is the difference? Here is the actual pressure, that is the saturation pressure for the same, at the same temperature. What this mean here? For the same temperature T, this PV represents this point, and this point represents, no, this is actual, this is maximum at that temperature. So this is PV, and mass here and mass here, mass of water vapor here and mass of water vapor here. This ratio is called relative humidity. Okay, at that particular temperature. Okay, so now volume will cancel, T will cancel, or V will also cancel because it's vapor. So it means specific humidity can be, sorry, relative humidity can be defined in terms of mass or in terms of pressure, but only vapor or water. Okay, that is relative humidity, where Pg is actually Psat at that temperature, this Pg on the saturated curve. So relative humidity, we normally define it in percentage. So pressure of water vapor divided by saturation pressure of water at that temperature multiplied by 100. Okay, so that is clear. Now, if we can solve these two equations to derive this one, we did this derivation in Thermo 2, so I will not do it here. So here is relative humidity in terms of specific humidity. Or we can also write the same equation, specific humidity in terms of relative humidity. Now, what is P, Pg? Hopefully, it's clear. Only P, yes.
W and WS, WSA and WS is PMR for the humidity.
W,
Is A. Same as base symbol.
I do not understand.
Or H, PW or PWS. You would say that PWS is equal to PG.
Yes.
So,
Here, this P is total pressure.
now this is for relative humidity.
Yes, this one. Yeah, this one.
Yeah.
Actual pressure of water, saturation pressure of water
Same for
at a particular temperature. This one. Ts at one particular temperature. For example, this is the actual water vapor pressure, this one, at the same temperature. And this is the Pg. This is Pw, this is Pws, saturation. Okay, the same is also represented by Pg. Okay, clear? Okay. Here we can derive some more equations where derivation is not included to find out humidity, relative humidity, and specific humidity. Okay, but in this course, we already did these equations in Thermo 2. Here we shall only be using charts to find out all this. Okay. There we used equations already. Only charts. Charts is better. So using those equations, they have developed those charts. Okay. So I want to reach that chart as early as possible. Okay. Yeah, we have discussed this one. Okay. Relative humidity minimum is 0, maximum is 1, or 0% or 100%. Okay. And that can be changed with temperature. Okay, so we'll start from here in the next class.
Lecture will be late maybe for 10 minutes, 5 minutes, because I have materials.
Okay, I'll do it.